Assalamualaikum and hi. We meet again for Chapter 3, Rate Law and Stoichiometry. This is part 1 of the lecture. Before that, I would like to explain the reason we are doing these video lectures. We prepared this material so that you are able to learn at your own time and pace. Plus, we have a very short duration of 14 weeks. So in order to ensure you could understand each topic and have time to do problem solvings, you need to prepare before coming to class. So during recap session, you can strengthen your understanding and ask questions that need to be clarified. Then we can have more class exercise and problem solving. But if you prefer to study using the lecture notes, I have also stated which page number of the textbook that you can refer to so that you can study without referring to the video lectures. Okay, so this is the main textbook you can use to study, and also there are a few other additional references that you can refer to. So please go to the course outline and you will see there is a few recommended reference for you to study, to use. Let's first recap what we have learned so far. So in chapter 1, we learned on how to develop mole balance design equation from general material balance equation, and we look into different types of reactor. And then in chapter 2, we establish the equation for conversion for both batch and the flow rate and the flow reactor. Then we rewrite the design equation to calculate the volume in terms of the conversion, while for batch to get the reaction time. And lastly, we do reactor sizing based on the given information of the reaction rate in the function of the conversion. Okay, so this is the learning outcome of chapter 3. So chapter 3 also addressed to CLO number 2. CLO number 2 of the course, which is to apply the principle of chemical reaction engineering. Principle of chemical reaction engineering in problem solving. And this CLO address itu to PO. PO number 2 and PO number 3. So PO number 2 is on the analyze the problem, and PO number 3 is design the solution. So by end of this chapter, you should be able to define the rate law, reaction order and stoichiometry, set up the stoichiometric table, and lastly apply the concept of stoichiometry, reaction order and rate law to solve reaction engineering related problems. So in reaction engineering, we are dealing with 4 types of reaction. Homogeneous reaction involves only one phase, and the opposite of the heterogeneous reaction, which involve more than one phase, and the reaction usually occurs at the interface between the phases. And while irreversible reaction proceeds in only one direction and continues until all reactants are being consumed. And the opposite to irreversible reaction is the reversible reaction, which can proceed in either direction depending on the concentration of reactants and product. Before we move into problem solvings, there are few terms that you must understand. Okay, so the first term is rate law. So rate law is given by this expression. Okay, rate law is given by this expression which describes the behavior of a reaction And rate law is affected both by the concentration and also the temperature. So rate law can be used in both elementary and non-elementary reaction. Okay, so consider this reaction A plus B to produce C and D. So the capital letter is the species involved in the reaction, and the small letter is the stoichiometric coefficient of the species. So the rate law as a basis of A is this one. Okay, so another term that you need to understand is the relative rate of reaction. Okay, so consider the same equation. You have relative rate of reaction of a species in a reaction is related via this equation. Okay, so the reaction by this equation, so the reaction rate is divided into its own stoichiometric coefficient. So negative minus RA and minus RB, showing that these both reactants are being consumed, and RC and RD is showing that the product is being produced. Thus the rate of the reaction of species B in terms of species A can be written as minus RB equals to B over A is the stoichiometric coefficient times the minus RA. So if you're looking into the relationship between rates of formation of C and D, so we can write RC equals to C over D times RD. Okay, so the next term is reaction order. So reaction order for this equation, for this reaction, A plus B producing C and D can be written in terms of this. So alpha is the order in A, and beta is the order in B. So the overall reaction order is equals to alpha plus beta. So this reaction order is determined by experiment. So reaction order refers to the powers to which the concentration are raised in the kinetic rate law. Okay, so look at this example. Consider a reaction of A to produce products. So the general expression of rate law is given by this equation. So we have minus RA equals to KACA to the power of alpha. So minus RA is the rate law, Ka is the rate constant, and alpha is the reaction order. So for example, if you have first order, so this is only 1. So you have minus RA equals to KACA. If second order, alpha equals to 2, and third order, alpha equals to 3. Okay, so this is the units for rate constant K. So unit of K depends on the reaction order. So here we have the same unit for the concentration. We also have the same unit for the reaction rate. So what's different is the unit for the rate constant. So you need to know which reaction order have which unit. So you'll be able to identify what is the reaction order when you do problem solving. You have learned about the elementary and non-elementary reaction in your foundation. So this is just a recap. So elementary rate law involves a single step reaction, and the stoichiometric coefficient equals to the individual reaction order of each reactant. So for example, you have A plus B producing C and D. So the rate law here, since you have only A and B, so it means the stoichiometry is 1A plus 1B. So the rate law is minus RA equals to Ka to the power of 1 and KCA to the power of 1 and KCB to the power of 1. And for non-elementary rate law, can be in homogeneous reaction or heterogeneous reaction. So for example, it involves reaction where the overall reaction order is not an integer, and it also can involve free radicals, and also involve reaction in a solid catalyst process. Okay, so before we move on, let's just check your understanding so far. So consider this elementary reaction B plus 2D to produce 3T. Which of the following is correct? Now we look into a reversible reaction. So considering you have this reaction A plus B species B producing number of C species C plus number of D species D. So at equilibrium, reaction rate for all species is the same. So the rate net will be equals to 0. And the concentration of species at equilibrium are related by the equilibrium constant. So in equilibrium reaction, you will have equilibrium constant. Okay, so another term is the reaction rate constant, K, and the activation energy. So rate constant K depends strongly on the temperature. So you have learned about the Arrhenius law. So this is the equation to calculate the rate constant. And the activation energy is the minimum energy required for a reaction to occur. So the larger activation energy means the reaction is more sensitive to temperature, and activation energy is determined from the experiment data. Okay, so activation energy is determined from the experimental data of the same reaction that carried out at different temperature. So Arrhenius law is represented by this equation, and you rearrange the equation to get the y equals to mx plus c, and you need to plot the graph of ln k versus 1 over t, and you will get the slope as the value for minus e over r. So the steeper slope indicates higher activation energy, which is means the reaction is more sensitive to temperature. Okay, let's look at this example on how to determine the activation energy. So you are given a data of K and also the temperature. Okay, so first you write down the equation for the Arrhenius law in terms of the linear expression. So you will have ln K equals to ln A minus e over r times 1 over t. So ln K will be your y, and 1 over t will be your x. Okay, you plot a graph, you will have a straight line, and here you have, from the equation, you will have ln A equals to the C, which is 38.925. So to get the A, you just inverse this value, and you will get the A. And to get the activation energy, so you have E over R equals to minus 14612, which is in unit Kelvin. You can also calculate the slope of the line, so you will get this value, and R is the constant, so you will get the value of E, which is equals to. Okay, now we look at the last term that you need to understand. So stoichiometry is to relate the concentration of different species to each other for a single reaction. So let's say you have this general equation, A plus B producing C and D. So taking A as the limiting reactant, this is the relative rate of reaction. Okay, so what does stoichiometry tell us? So a complicated stoichiometry usually indicates multiple reaction. Okay, for example, this equation. And the second thing, the indication if a reaction is elementary. So molecularity greater than 3 indicates that this reaction is non-elementary reaction. And last one, the comparison between stoichiometric equation and experimental kinetic expression indicates if a reaction is elementary or not. Okay, so we have come to the summary part of this lecture. What I would like you to do is I have provided all the terms that you need to understand. So your job is to write down the definition and the important information of each of the term that we have learned in this video lecture. Okay, so thank you for watching. So in the next part of the video, you will learn how to use all the information and definition that we have learned here.